very, very important because you as innovative startuppers must have a deep insight of the problems that you want to solve, but also the technologies that you want to use as a leverage to solve those problems. It will be tough. I know it will be tough. So I will try to be I'll try to speak as simple as possible and to be as entertaining as possible too. In fact, the slides are hand-drawn by myself, so you'll at least enjoy my doodles, I think. So this is me. As you can see, I'm a very good drawer. It depicts perfectly me, especially the nose, it's perfect. As was stated, my name is Anthony, and I'm a software engineer from Rome, Italy. I'm the founder, CEO, CTO, Intern of Inglorious Coderz, which is a fistful of heroes striving to create a better world through better software. Actually, this is what I want it to be, but for now it's just a one-man army. It's just me. I'm a freelancer, that's it. But I really love to write code and teach code. So that's what I do for private startups and also big businesses. I help them develop their solutions in the most simple way as possible. As for you, what's your name? No, not great. As for you, I assume that the audience consists of two kinds of people. The tech-savvy guys, the engineers. So those who know how to program. How's it? Yes. This is you guys. How many engineers or developers or people that know how a shell works? Raise your hands, please. Okay, not so many, but I expected that, and I'm glad. I'm really glad of this, because actually this talk is intended for the other guys. So please don't leave. I hope you'll find my words at least relatable, but this talk is intended for the other guys, the non-tech savvy guys. I want to give you some high-level information about what technology is. And since it's going to be very tough, I really demand you some immediate feedback. So I know it's early in the morning and you're also sleepy, but I would like to see some visual feedback from your faces and from your gesture. For example, if you find what I'm saying interesting, you can do something like, if you find something funny, you can do, okay? And if I speak too fast, you can use this. Slow down, come on. And if you are completely lost, if you don't understand something, you can use the Italian question mark. What? Okay? So, I hope you will not be like these three guys that just do what they want and don't listen. Okay, so let's start with it. The first thing I want you to know is that technology is hard, of course. It's not only hard, it's complex. It's such a complex problem-solving activity that in order to solve a problem, we have to split it down into multiple sub-problems, then solve those problems independently, and then join the solutions back again to have the overall solutions. And we can split into multiple levels, which are usually called layers. The problem is that those layers are not like the layers of a cake. They're not so tasty. They're more like abstraction layers, so they look a lot more like this kind of stuff. At the lowest layers, we solve the most low-level and technical solutions. In fact, here you can see transistors, resistances, etc. But the higher you go, the more high-level, the more high-level is the solution you are facing, and the solution you are facing, you are building, relies on the lower levels. So the more you go up, the more you can abstract and focus on higher-level problems to solve. Every layer speaks its own language, and I'm dividing the languages that we use in three main categories. The low-level languages, such as this one, are, for example, assembly or C. Are languages that operate directly on the machine. They are very low level, and they speak a language that we usually cannot really understand. It's more like a language that a machine can understand. I could make an example of a sentence in a low-level language, which is, take a value from an address in the register, take another value from another address in the register, then sum them up and put the results in another address. You can see that you cannot build web applications with this. It's way too low level. But on top of these low-level languages, which are still widely used for high-performance computations because they are blazingly fast, On top of them, we have high-level languages such as Java, Python, JavaScript, Ruby, you name it. And these languages speak like me, like a nerd. So they are high-level, but they're not really human-readable sometimes. Maybe Python a bit more. An example could be iterate over a list of users, and for each one print their names. So pretty understandable, although you have to put brackets and semicolons. On top of these languages, we have the highest level of languages, which are usually called markup languages, or even visual languages. These can be used by pretty much anyone. And they are very easy, so they allow you to build user interfaces mainly. The problem is that once you have your static user interface built, when you want to add some behavior to that user interface, then you have to rely on at least a high-level language. So you have to program. It's not just, you can do anything with just markup languages. Okay, let's have a look at the technology stack that we have on modern devices. The technology stack, which means all the layers that we have. Do you recognize this thing? What is this? You're so young. Okay, maybe it's me that I don't draw too well. It's Tamagotchi. Do you remember the pocket monster you have to nurture it? Okay, the Tamagotchi is an example of an old electronic device. We have VHS recorders, etc. These electronic devices are electronic devices, they are not computers, because they are programmed on the machine itself. They are programmed low level, and they do not have any operating system. This is the old technology, the old technology that took us to the moon, okay? Then we have computers and smartphones. The difference here is that computers have some hardware on top of which there's an operating system running. You know, Windows, Linux, Mac, or Android for phones, or other operating systems which are more, how do you say, exotic. When you run an app on Android, sometimes the app is not running directly on the operating system. It is actually running on a Java virtual machine, which is the simulation of a computer. It's a software that simulates a computer and that runs on your operating system. So actually, there are so many levels of complexity involved. In this case, you have an operating system which is running a program, which is a simulation of computer, on top of which we are running our app. So a lot of levels. And this topic of virtual machines is very, very used right now, because we can put many machines inside one physical machine. This is a pretty new stuff that we are dealing with today. And it gives us a lot of degrees of freedom. Then we have smartwatches, smart TVs. They're just less powerful versions of the usual technology stack that we have. We have consoles, game consoles. I recently found out that the modern game consoles are all computers. They are computers. They are usually a Unix-based system, except for Xbox, which is of course Microsoft Windows, but they are very powerful computers, nothing more than that. And then we have smart stuff, smart fridges, smart coffee machines, smart anything. They usually run some Java virtual machine, as I said before. Sometimes they have microcontrollers in them. And speaking of microcontrollers, microcontrollers are now a very trending topic because it's related to the Internet of Things. And they are just small computers without a case, without a mouse, without a keyboard, without a monitor. But they have everything that needs to run some software. So they have a processor, RAM, hard disk, etc. No, not even the hard disk. You usually plug a USB key in it. There are two kinds of microcontrollers usually. There's the Italian Arduino. I don't know if you ever heard of it. Arduino is very low level. You can program it like a Tamagotchi. So you can put a man on the moon with Arduino. And there's a Raspberry Pi, which is really a computer with an operating system that you can install on, and it's a computer, it's a real computer. You just have to put all the peripherals on top. So there are multiple layers. Well, you know this joke, it's not mine, but I try to recreate it. there are multiple layers, but we can roughly divide them into two main blocks, the front end and the back end. The front end is the piece of software the user interacts with, the user sees and interacts with, and it hides all the complexity and sometimes also the ugliness of the back end, which is all the rest, logic, the database, etc. To make it even more clear, there's not even a precise distinction, there's not a very precise line between front end and back end. It depends on your personal choices, the technology you're using, etc. But the back end has stores data. So this pie here is the depiction of a database, which is a very convenient way to store information. Then we have also some logic, which are those blocks there. The backend knows how to perform requests to external systems, that's the arrows that point outwards. And well, the front end, the presentation layer, has some graphical user interface. Sometimes it has some logic, sometimes it even stores data. So it's very fuzzy, the distinction is very fuzzy. One thing that is very important is that communication between all those layers is always from the top to the bottom, is always from high layers to lower layers. This means that a higher layer can ask for something, for some functionality to a lower layer, and the lower layer will give this functionality only as a response to the request of a higher layer, not the contrary. That's because this way you can build modular components that do not need to know anything about who's using them. They just give you the service, whoever you are. There is an exception to this rule, so communication can be also done from lower layers to higher layers. For example, if you think about push notifications, or if you have a computer, the CPU wants to warn you that it's getting too hot. So how does it work? Well, there are usually two mechanisms. One is polling, which means that a higher layer says, hey, are you hot? Hey, and now? Are you hot? Are you arrived yet? That's it. Or there's another kind of communication, which is sort of opening a persistent channel. So the higher layer opens a phone call and leaves it there. And then if the CPU, if the lower layer has something to say, he will say, hey, I'm hot. Oh, okay, I received. Okay? So it's a special mechanism that we use in some cases, but usually communication is from high to low. And how is this communication performed? Well, through an API. Have you ever stumbled upon this acronym? Yes, okay. API means Application Programming Interface, which I think is even more confusing than just saying API. Well, the crucial word is interface. An interface is how we interact with a subsystem. And everything can have an interface. We can have an interface. Cats can have an interface. If I want to pet a cat, I have to know where I'm allowed to touch it, or will I be scratched to death. For example, I cannot touch his tail usually, because he will kill me. If we split the front end and the back end into two separate computers, and we make those computers communicate through the network, we've built a client-server architecture. So it's very similar to the front end and back end, but we'll see some differences. When we split this code into two computers, we have to add some extra thin layers, just like when we split magnets. When we split a magnet, which has a North Pole and a South Pole, we have now two magnets, each one having its own North Pole and South Pole. And this is exactly the same. If we want to put the front end on the client machine, then we have to put a little thin layer of backend that knows how to communicate with the other machine, with the server. And as for the server, it will have the backend, but it will also need a thin layer of front end, which is the API layer with which the client can communicate with it. So, as you may have understood, client and server is two machines communicating just like layers from top to bottom, but through the network. There are some other differences, of course. The server is usually a central server, which holds all the data and all the logic, and clients, various clients, can communicate with that server. But it's not only like this, it's just a role. The server is just a role. So you can have a machine that behaves as a client and as a server, both of them. It's a server for someone and it's a client for someone else. A server can be accessed by multiple clients, but a client can also, where is it? Here. A client can also ask for information and functionalities to multiple servers, okay? So this is usually the mainframe architecture, and it's very convenient because now clients do not need to hold information or behavior. All the information and behavior is centralized in a central server, and clients can be, they are called thin clients, because they just need to hold the presentation layer. This is very convenient, but it also has its drawbacks. For example, if the server fails, no client will be able to do anything at all, because they rely on something that failed. So there are the solutions that allow us to have something more stable and more resistant, more resilient. One thing that we can do, for example, is clients do not access directly to a server. Usually they access to a particular server which is called load balancer, which balances the load. It means that it dispatches all the requests to various servers which are hidden from us. So we have an API that hides all the complexity of this. We just seem to call a server while we are calling multiple servers instead. If this was complicated, you won't like this slide. So this is the worst slide that we have. It's very complicated. But this is the usual situation we have nowadays. We have a browser with a website, a web page, that wants to access some information. So the browser will perform a request to the so-called web server, which serves web pages through the internet. Unless you want to build static websites, if you want some logic, the web server will probably ask this logic to an API server. And the API server, in order to perform these computations, will maybe ask a DB server, a database server, to get those data. And this was until the 90s. This is so Web 1.0, but we are now in Web 2.0 or even 3.0. So right now, the browser, along with HTML web pages, is able to download some JavaScript code. And JavaScript code is run directly on the browser. This means that the browser can now call directly the API server. So the logic can be split between the browser and the API server. The web server is just a very basic server that serves web pages, nothing more. But then the browser will speak directly to the API server. And what if we want some authentication? Well, we can ask an authentication server, and this can be accessed by the web server or the browser. It depends on your choice. And the authentication server must perform some computation to authenticate a user, so maybe it has its own API server to ask. And the API server could ask for user accounts to its own DB server. And when you want to create push notifications, well, there's a push server, etc., etc., etc. This is not even the most complex architecture. It can be a lot more complicated than this. And I don't even want you to understand every bit of it. I just want you to know that it's complicated. Okay? Is it complicated?
Yes.
Okay.
Too many servers.
Too many servers. An alternative, which is quite trending nowadays, is the peer-to-peer architecture. So there's client-server architecture, there are many other architectures, and this one is very important because, as you may know, it's strictly connected to the blockchain technology, which I will discuss later. So in the peer-to-peer network, every node, they are called nodes here, neutral, acts as both client and server. And they also store information. This is a very resilient network because once once a node has downloaded some data, it shares it with other nodes. And if a node fails, a client node can ask for any other node that has this data. So it's very convenient. Of course, it's a very redundant network because the information is replicated through not all, maybe, but many of the nodes. So the data is not centralized, it's distributed. So right now I think you can be a little confused. You are here to build your innovative solution, you want to build a website, an app, or some hardware stuff, and I haven't talked about anything yet. But I think that these bits of information are quite useful to understand what is going to happen later. So, if you ask me, what do I have to use? What tools do I have to use? Do I have to build a website, or which framework, CMS, etc. I have to use? I don't have an answer for you right now, because it depends a lot on the problems that you want to solve, the technology that you want to use, what you are capable to do, etc., etc. Even how much it costs or how much it will take. By the way, this is a deadline. Okay, so first of all, you have to buy a domain name. You usually have to buy a domain name. A domain name is just your identity, your presence online, and it's the only thing that you have to pay upfront. You cannot have a domain name for free. Well, yeah, some domain name registrars actually give you a domain name for free for the first, I don't know, year, and then they charge you for the rest of your life. So, buy a domain name. Facebook bought Facebook.com, of course, but they also bought other similar domain names. For example, Facebook.com with just one O. So when people mistype the address, they get redirected to Facebook. This prevents phishing and allows the user to get where they want with no hassles. After this, you have to build a prototype, and Zaid will talk about prototypes. The prototype will look good, will look beautiful, but will be fake. So don't get too affectionate to this prototype, because at a certain point you will want to get rid of it and build the real thing. Okay? When you want to build the real thing, you have two choices: build it by yourself, or maybe outsource it. Pay someone else to build your prototype. This is a Falcon. Watch out, because when you ask someone else to build your prototype, you have to rely on someone you trust. The problem with technological solutions is that you don't want just an app. First of all, you want an ecosystem of softwares that interact with each other. You want an app, you want a server that holds your data and some logic, you want maybe an administration panel, a back office platform for your business to run the app, to customize behavior on the fly, etc., etc. So it's not just an app. Remember, there's a lot of things involved, such as you know, there's marketing involved, commercials and design, etc., etc. There is also a lot of stuff involved in technology. And also, the technology that is built is not a one-shot technology. You want to change it over time. You want to evolve it. So pay attention, because sometimes you outsource your code and they do a good job for a start. Then maybe they give you the source code and you find that inside the source code is crap. You cannot change it, you cannot read it, it's unfeasible, and you have to start all over. You bought cheap, 5,000 euros for an app, yay! And then you have to start all over again and pay 30,000, 60,000 euros for a real app that works and that can evolve over time. So, watch out. One thing that I suggest you is to keep everything in-house. The source code, the passwords, and the know-how. In fact, what I usually suggest is that you need to have one CTO. Maybe it can also be not too technically skilled, but enough to deal with the suppliers, and then to go on by himself or herself when the time is right. Okay? So what I usually do as a consultant for startups is I'm not building the app for you. I usually help your CTO building the app. We are building this together, and then after a month or two, I will make sure that you can get rid of me, and you can go on by yourself. I think that this is the most sane way to work. If you want to do everything by yourself, you're welcome, but pay attention, because you have to deal with the steep stairs of abstraction layers. I put some 4 words here. On the top level, we have content management systems, such as WordPress, Joomla, or PrestaShop for e-commerce, etc., Magento. Have you ever heard about one of these? Yes. Okay, good. So, content management systems are good if you want to build a website or an e-commerce platform. The problem with these high-level solutions is that they are not very customizable. So, if you can put plugins on these CMSs and trigger some new behavior, some custom behavior. Sometimes, if your software is very specific, you have to build your own plugins. And you have to build them usually using coding in PHP. I don't know if you like PHP. You like PHP? The only one? No. Okay, there are some PHP developers. I hate it. But the problem is that it's still quite difficult to get inside the internals of the CMS to build a plugin. And CMS are generally slower than custom solutions because they have to deal with any kind of problems. So they make huge round trips to get to the point. Well, when we build custom solutions, they get straight to the point. If you don't want to use a CMS, but you want to code, you can use a platform. For example, if you're building a mobile app, Android, iOS, you can use the Android platform or the iOS platform, which is an ecosystem of tools, including a text editor that allow you to program with everything you need to get started from the start. But you have to, of course, learn a lot about the platform, the programming language you are using, etc., etc. There's also Flutter nowadays. I think that we will suggest Flutter to someone who wants to try it. On a lower level, we have frameworks. So we're not relying on platforms. We use our own editor, our language of choice, etc., etc. But we don't want to make everything from scratch. We want to rely on a framework. A framework gives us some functionalities right out of the box, and also some structure. They give us an architecture that we can rely on, that we can follow. They give us best practices, so we're not completely alone by ourselves. And on the lowest level, we have libraries. We can use libraries inside frameworks too, which are pieces of code that do something for us. For example, if we want to put some charts on our app or on our web app, well, there are charting libraries, so we don't have to draw charts by hand. We just put the data, and the charting library will do the rest for us. As for the process, during the product sprint, and also in real life, I suggest you to go both incremental and iterative, which is a little different from what you have heard maybe till now, because they usually say go iterative and not incremental. But in software, you have to do both. So you know already that incremental means that you start from a piece of your software, and then you build another piece incrementally until you have the final product. The drawback with this is that the client will be satisfied only at the end of every cycle, of the last cycle, sorry. So what I suggest you here is to use very short cycles, iterate, increment continuously, and stop and complete them as quick as you can. You have to go also iterative, which means that on each cycle, you're not creating the solution you had in mind, but still a solution that user can enjoy immediately. So, for example, if you want a car, you can start with a skateboard and then go with other kinds of solution, and the user will enjoy every solution that you have on the cycle. For the incremental part, I think that you should not start from the wheel of a car. Maybe you should start from the body, because it's something that the user is able to see, at least. So, what I'm suggesting you here is that, even in the product sprint, you should start from the highest layers. You should start with the visible content, fake it till you make it, and then progressively build the internals. So you will have a static app that does nothing, then you will add some logic and maybe some fake data inside the client, then you will be able to build the server, etc., etc. So very progressively. And don't start from the login page. I think that many people told you already by now, the login page is something that every app has, and it's not important. But we don't care about the login page. If you want to create an app that deals with, I don't know, taxi booking, start with the search of taxes or payments or something that is not the login page. As for apps, apps are created by you, by your supplier, and then they are installed on the Play Store, the Apple Store, and then you have them on your phone. Once you have downloaded them, they are there. But sometimes, usually, they have to communicate with a server. Now, a server must deal with a lot of problems, mainly identity. Authentication is a very hard topic to tackle. So, if you want, you can build your own server, which is just a machine. You can run your server on your laptop. The problem is that your laptop should be on 24/7 and should be able to handle all the requests that are coming from your users. So you have to deal with problems such as high availability, scalability. There's a lot of things involved, complex engineering stuff. So sometimes it's better to run your code on the cloud. Did you understand this reference? Yeah. Go. Yeah. Okay. Dragon Ball. Okay. Not Tamagotchi, but Dragon Ball. Yes. Okay. So if you want to run your code on the cloud, there are many services out there that you can call through APIs. You already know about, I don't know, Google Cloud, Amazon Web Services, Microsoft Azure. Every major business company has its own technology stack for this. They are pretty much very convenient actually, because when you want to try them, they usually have a free plan, and when your business starts growing, then you start paying proportionally to the user base you have. So it's quite good. And there are also higher level and lower level services, so it's up to you which ones you want to use. So by now you should be able to understand some of the buzzwords that are in the air lately. For example, the serverless architecture, it's an architecture that does not mean it's without a server. There is a server, but the server is not managed by you. There is an external service, for example Google Cloud, that provides you the server, so you can focus on your client only. Okay? Microservices. Microservices is just splitting the code of your server into multiple servers that communicate with each other. So every single server does one thing, but does it well. And you can combine all those servers together to get new functionalities, because you have modular components that you can move around and make them speak with each other in different ways, maybe new ways that you haven't thought about before. Then we have IoT. I already said something about IoT. It's just putting a computer with a network card and some sensors inside every physical object. IoT is strictly connected with big data, because sensors will hold a lot of information that we then have to manage. We have to do insight on those big data. And big data is usually tackled with machine learning, which is a branch of artificial intelligence. Groby is an example of artificial intelligence, sort of, but it's mainly a conversational UX. So this is a cool thing. You don't need to build an app or a website to perform some functionalities. You can chat with a robot. It's very easy to implement graphically wise, because you don't have to build anything from a user experience perspective. Everything is already there, and it's very easy to use for the users too. Even elders can use them very easily. Then we have VR and AR, virtual reality, augmented reality. These are so complex, so difficult to tackle, that I suggest you to rely on some supplier or some external service that does it for you. It's really too much. You cannot handle everything, all of it. Then we will talk about blockchain and quantum computing in the last slides. So about AI. In 2012, we witnessed a huge leap forward in AI, because someone came up with the so-called convolutional neural networks. So before 2012, AI could perform almost as humans. For example, optical character recognition, they perform sort of 80% of the times. They were 80% accurate, well, we are 90-something%. But now, with convolutional neural network, they perform better than us. And it's not just about computer vision. They can do a lot more than us. Before, they just passively recognized patterns. But nowadays, they are able to creatively build new content. So they are able even to compose music. They're able to do many stuff that I don't know how to do. I fear for my job. So AI is able to do deep learning. They are able to do computer vision, such as OCR, optical character recognition. They pretty much know how to speak with speech synthesis. They have always been able to speak. But nowadays, they can even give emotion. They can give intent to the speech. So they are almost humans, sometimes even better than humans. And they know pretty well how to recognize the words that you speak. And of course, you know it because you use your Siri or your OK Google, etc. And with natural language processing, they are even able to really understand the words, the phrases that you were saying. If you want to do some AI, there are two choices here, I think. One is to use a library called TensorFlow by Google, which is in Python usually, and but you have to study a lot about convolutional neural networks, etc., etc. It's a very complex task, and you also need a lot of computation power. These neural networks, in order to be trained, need a lot of CPU. So much CPU that we do not use CPU anymore. We use GPU, which is the processor inside graphic cards. So we need a lot more cards than before. We need a bigger computer, much more expensive, etc., just to train the neural network. Or you can use some ready-made service. IBM Watson, the Google Cloud Services, etc. There are a lot of solutions out there that tackle the most common problems. If you have a special problem, a custom problem, then maybe you have to hire someone who's expert in AI. But for the most part, you can use some ready-made service. What about blockchain? This is a very common buzzword. Everybody wants to create a blockchain. Well, a blockchain as a technology is just another way to store information. And in this case, it's represented as, surprise, surprise, a chain of blocks. That's it. Usually, traditional databases store information as data. For example, an amount of money or a phone number. Blockchain stores information as the transactions that operate on this data. For example, an amount of money was transferred, or a telephone number was added, something like this. Every transaction, or to be precise, every batch of transaction, is then added to a block, which is added to the chain by a miner. They are called miners because they mine new blocks over time. And this block has a unique ID, namely a hash, which refers to the previous block, and is tightly coupled with the previous block. So the blockchain is unique with these unique IDs. Well, the blockchain relies on the peer-to-peer network. So if I have a blockchain and I add a block, I usually share the new blockchain with my peers. So everybody has a copy of this blockchain, which is, as we said, a more robust, resilient solution, even though it's a little redundant, as we said before. What if two miners concurrently build two different blocks? Well, we have a problem there, we have a conflict, but this conflict is already solved automatically by the blockchain protocol. It solves the conflict automatically by promoting usually the longest chain, and that's it. And that's it, this is the blockchain. Now, if you want to do something more, you may think about some problems that you want to solve with it, or some problems that this architecture arises. For example, if my phone number is shared by all the peers in the network, does it mean that my phone number is public? Well, no, if you use encryption, because you can have a replica of your data in others' computers, but with encryption, no one will be able to read it unless those who have the key. Or how can I make sure that the miners will create valid blocks, blocks that are valuable for my network? Well, you can give a little compensation. You can give some money to the miners that create valid blocks. And this is exactly how Bitcoin works. Miners will be rewarded with some small amounts of money for every block that is created. So blockchain technology is quite good as a technology, but it has its drawbacks, of course. For example, one thing is that it's very slow. We are making advances in this topic, but blockchain is still quite slow. So in order to have a valid blockchain, you have to wait 10 minutes. You cannot build video games with this. You cannot wait 10 minutes for every move you make. And it also is quite big as a hard disk intensive, because every node has the copy of the blockchain, which is the history of all transactions from the start of time to now. So it can be quite heavy on your hard disk. Finally, quantum computing. This is very, very new. It's still an experimental technology, but I think it's quite a good thing to start talking about it. Well, quantum computing, apart from the technical details, it will allow us to solve those problems that usually require trying every possible solution in order to find the right one. Such as this guy will try all the keys in order to find the right key to open the door. Well, quantum computing just tries all of them simultaneously and opens the door instantly. Well, this is an oversimplification actually. It's not true. The truth is that with Grover's algorithm, the quantum computer will be able to take the square root of the time that it usually involved in dealing with those solutions. So it's pretty fast. Does this mean that we will be able to break passwords? No, because usually websites have, you can try 3 passwords and then they block you. So it's not a big deal. You can block this behavior on the front end. But they are able to break encryption. So we have to deal right now with quantum resistant encryption methods. Because one day, quantum computers could be able to break the internet otherwise. So that's it. That's what I wanted to tell you. I hope I gave you some new information, some inspiring information. I hope that the sexy unicorn you were trying to reach is a little nearer. So thank you all, and we'll see you around. Thank you.